Great. Okay, thank you very much, everyone, for coming. This is the 11th in our series, Tunneling in QFT, and the last one of the year. We're planning to continue this in the new year, but haven't yet scheduled the first few months. So if you'd like to give a talk, or you know someone who would, please send them in our direction. Today we have Joonas Hirvonen from the University of Nottingham, who's recently started as a postdoc here, and earlier this year completed his PhD on pretty much the field that he's going to talk about today. Tunneling at finite temperature stuff. Joonas, very much looking forward to hearing your talk. Please take it away.
Okay, thank you. Thank you for the possibility to present my work, and thanks for everybody joining in. So I will be talking about real-time nucleation and off-equilibrium effects in high-temperature quantum field theories. So the overview of the talk will be the following. First, we start with an introduction, setting the talk into the greater scheme of first-order phase transitions in the cosmological evolution of the universe. And we will cover the aims of this talk and also give the general physics picture. Then we will discuss the system at hand, which is described by high-temperature quantum field theories. And in particular, we will discuss the split of the system into particles and classical fields. And after obtaining the equations of motion for the whole system, we will discuss classical nucleation theory, which will then enable us finding the rate at high-temperature quantum field theories. So, first, the introduction. We will discuss the cosmological first-order phase transitions and the links between nucleation rates in those and gravitational wave signals. We will overview the aims and discuss the general physics picture. So these cosmological first-order phase transitions, they take place by nucleating bubbles in primordial plasma. There are none in the standard model, but plenty in standard model extensions. And they could, for example, explain the existence of matter in our universe by giving a mechanism for matter production. For example, the electroweak baryogenesis. And in addition, this nucleation, it shakes up the plasma, primordial plasma, which then leads to gravitational wave signal. And this might be observable in the future, for example, with missions like LISA, giving us a possibility to peek into the early universe with these phase transitions. So these gravitational waves, they are pretty sensitive to nucleation rates. And the link between the rates and gravitational waves was discussed in the previous talk by Mark to some extent. And so these nucleation rates, they kind of give the setting to the transition. So they dictate the duration of the transition, and they also pretty much dictate the nucleation temperature or the transition temperature. Here, it is affected by the rate directly and the duration, but also this expansion velocity of the bubble walls. But it's dominated by this rate because it's an exponential quantity. There was an article by Oliver Gould and Tuomas Tenkanen, where they looked into the gravitational wave spectra of a model, and they did perturbation theory more precisely than before in this model, and they managed to shrink down the uncertainties in gravitational wave spectrum by quite a bit. But there's still this remaining uncertainty, which is mostly due to gravitational waves, nucleation rates in this gravitational wave spectrum. So it would be still desirable to be able to do nucleation rates more precisely. And this is something that we are aiming to do here, going towards precision nucleation. So what I'm discussing here is the first analytical study of equilibrium plasma particles directly affecting bubbles and their nucleation. And what we will find is that it backs up equilibrium studies up to a certain validity. And it also sets up further studies with standard model extensions. And it also gives tools assessing for the validity of current nucleation theory. So these are the general messages that I wish to convey during this talk. And the general physics picture is the following. So there's a bubble nucleating in the plasma, and it is showered by thermal particles, which gives kicks to its evolution. And this bubble, while it's growing, pushes these particles out of equilibrium. So here I have a plot of particles coming from the left, and the bubble is growing, and it pushes the particles out of equilibrium, which then gives a back reaction onto the bubble, slowing down its evolution. And consequently, it will also slow down the nucleation rate. And this is the general picture of the particles showering in the bubble, and then bubble evolution driving them off equilibrium, which then slows down nucleation rates. So now we have the general physics picture. Let's us look at the system more carefully. Because weakly coupled quantum field theories at high temperatures. Firstly, we will lay down an example quantum field theory model for concreteness. And then we will discuss the thermal system, and it's split into classical fields and particles, and find the equation of motion for the thermal system. So the example quantum field theory model that we will use for basis of understanding is a real scalar field that's coupled to a Dirac fermion. So here is the it's a basic real scalar field theory with renormalizable terms, and also the regular Dirac fermion, and then there's Yukawa interaction between the fields. And the real scalar field is the one that will nucleate. It will undergo the phase transition. And the Dirac fermion provides plasma particles that interact with the bubble. And the interaction comes through the change of the mass of these particles. So the bubble background and its evolution change the masses of the particles, so it will affect their movement. The same actually happens with the real scalar. So it's not only undergoing nucleation, but it also provides plasma particles that as well interact with the bubble by having their mass changed because of this background. The power countings that we will lay down will be kind of vanilla. So we assume perturbative couplings, but we also assume that there are no coupling hierarchies, no mass hierarchies in vacuum. But at the phase transition, this will lead to a high temperature scale hierarchy. So the temperature will be much higher than the masses of the fields in vacuum. And this is in general because of the phase transition is initiated because of the thermal fluctuations change. And so the thermal effects that come through perturbation theory must be of order of the tree level Lagrangian parameters. And hence there will be this high temperature hierarchy. And so we are interested in this thermal plasma at high temperatures. So there's thermal energy and excitations, which leads to a plasma system. There are, of course, plasma particles from both the Dirac fermion and the scalar field. But there's also this long-range classical bosonic field that comes from, which can originate from any light, or which will come from any light bosonic fields. For example, this phi field. And let's discuss these classical fields first. So they live in this long wavelength regime and correspondingly they occupy low energy states, so they are low energy. And these fields are classical because of the large occupation number of the bosons in these low energy states. So because of the correspondence principle, they are classical. And as said, there's one classical field associated with the phi field. Here's this effective description for it. The left-hand side is the basic Klein-Gordon form, augmented with this thermal potential that we will discuss shortly. Then there's also this off-equilibrium term. Here are off-equilibrium plasma particle distributions that's coupled to the field through the mass change. And these particles, for the example at hand, they are rescalar and Dirac fermion particles. So this is the effective description for the phi field. The effective potential that's in there is a previous work of me and Oliver Gould. So we argued that one should coarse grain the system, leaving the bubble scale intact, so that the potential can still describe these dynamical bubbles. But this coarse graining also induces thermal dependency into the effective potential, which then initiates the transition. So initially we are in this state, and then the other state becomes stable, and then there will be a first order phase transition between the potential minima. For the example that we laid down, this corresponds to coarse graining corresponds to integrating out this scale of energy scale of temperature. So it's, in sense, they are the particles being integrated out. And this corresponds to high temperature dimensional reduction in the context of Euclidean field theories or equilibrium field theories. And the resulting potential for the example will be of this form. So there's a mass term here that gets thermal corrections on top of the bare potential mass term. And also there's a linear term induced by the thermal fluctuations. Now let's just move on to the thermal particles. So they occupy this regime of energies of order temperature, and they are described by particle distribution functions whose time evolution is given by Boltzmann equations. So the left-hand side of the equation is the collisionless evolution, and then the right-hand side is the collision term that takes into account two scatterings on the leading order of these particles. And importantly, there's this force term on this left-hand side, which couples these particles to the background field because of the background field dependent masses. So this mass, spatially dependent mass, kind of induces a force field for these particles, deflecting their motions. Now, this collision term that I mentioned being in the Boltzmann equation is actually a problematic term for the analysis at hand. It introduces dissipation without noise, and because there's dissipation without noise, the system asymptotes to a flat configuration, and if we are flat in the metastable state, there will be no nucleation. And hence this equation cannot actually be used directly to do our analysis that we will do. In the example that we are using, conveniently, this collision term can be approximated to be 0. And this is because the collisions are important only on this really long length scale here. And we are interested in nucleation, so we are interested in the size scale of the nucleating bubbles, which are given by the mass of the field. And that's on a much shorter length scale because of the perturbative couplings. And so we can ignore these collision terms. In general, the importance of collision terms only happens if there's a hierarchy of couplings, And for example, the QCD coupling is stronger than many other couplings, and so it can induce this hierarchy where the collision terms become important. I will argue at the end that this is actually not a limitation of our result, and we can actually handle these collision terms, but we will only be able to add them in post-production. We are interested in the off-equilibrium particle effects, and so let us have an equation of motion for these off-equilibrium particles, and this happens by subtracting of this equilibrium distribution. Now, importantly for us, this equilibrium distribution is time independent. It's in general space-time independent, but the time dependency will be the important factor here. And the space-time dependence comes through the mass that's dependent on the background bubble, which is a dynamical bubble. So the masses of the particles depend on the location and the time. And this enters here in the equilibrium distribution. And deriving the equation of motion from the Vlasov equation for these off-equilibrium particles, we will see that there's this this source term coming from the evolution of the background field. Here we have also dropped off the force term, and it is because the force term will be negligible for these particles because of the high temperature scale hierarchy. Okay, let's now summarize the high temperature system. So it splits into fields and particles, and these off-equilibrium particles and fields, they are coupled through these terms. We will see that the whole system is actually conservative, but large field changes are effectively dissipated. So if we have a bubble that's nucleating, it will have this term being induced by the change in field value, which then again induces a change in the off-equilibrium particles. So they will be pushed off equilibrium, and then this term will dissipate the field motion because it gives a back reaction. Okay, now that we have the description of the system at hand, let us review classical nucleation theory, which will then give ingredients for solving the nucleation rates for these equations of motion that we have. Firstly, we will go through the setup and assumptions. Then we will see important field theoretic structures, and then finally discuss Lange's rate and contrast it to vacuum decay, which might be more familiar to some of you. So the setup is the following. There are two phases, one metastable phase and one stable phase. And this metastable phase is populated thermally, and the stable phase is empty. So this orange dashed line is the distribution function. This is a really schematic figure because we are dealing with a field theory, and it's actually living in configuration space and not, which is infinitely dimensional. We will hop into it later. But so the nucleation rate here is given by this thermal population evolving and leaking over to this stable state, and this will give us the nucleation rates. So this full system here is not analytically treatable, so we will make some assumptions. One thing is that we will zoom on to this potential barrier and only solve the system there, which assumes that the system can be linearized. So the perturbation theory actually holds. And another thing is that we assume that the rate is so slow that it doesn't really affect the equilibrium population in the metastable state. And so it's in a steady state and sourced by this equilibrium distribution on the side of the metastable state. But otherwise it's static. Let us discuss now a bit about Lange's, in which theories Lange was focusing on in his classical nucleation theory. The archetypal theory is given in here, and the general features are that it's local in space and time. It has explicit dissipation and noise given on this right-hand side, and the equations of motion are second order. So the analysis of Lange is more general than this equation, but this is a really kind of, it gives a good intuition on what we are talking about here. And we can contrast it against our system here. If this was second order equations of motion for the system, we could just use Lange's results, and that would be it. However, the particles that are introduced by this high temperature quantum field theory setting, their evolution is of first order. And so the analysis might not hold for the system. So we have to redo it for the system at hand. One could imagine integrating out these particles and getting this term directly based on the fields, but then it's actually not local in space and time. So one cannot really reuse directly Lange's results. However, overviewing it is really helpful, and eventually we will find out that the nucleation rate formula actually holds with small modifications in the parameters. So field theoretic structures that are relevant. We are actually in configuration space, as mentioned. Here's a 2D-dimensional slice of the configuration space. Metastable phase is on this side. Then there's a barrier because of the first order nature of the transition between the phases, and stable phases here. On top of the barrier, there's this transition surface that separates these two phases. And the nucleation rate is given by the probability flux over the surface. The important configurations that we will encounter are firstly the critical bubble, whose equation of motion is in here. It's this static configuration, and it's the lowest point on the transition surface. So you have to do better than the critical bubble in order to nucleate over the barrier. And another important configuration is this exponentially growing configuration around the critical bubble. So it kind of slides down the barrier towards the metastable phase. So it gives the asymptotic time evolution, and it's this like just barely nucleated configuration. And then onto Lange's rate. So as mentioned, the nucleation rate is the total flow over the barrier here. And integrating over the transition surface, one gets this kind of a result. So it splits into two pieces. There's statistical part with exponential suppression from the critical bubble and the fluctuations of the critical bubble. And this is an equilibrium quantity that me and Oliver Gould studied here. Then there's also a dynamical part of this nucleation rate, which corresponds to this exponential growth rates of this exponentially growing configuration here. So that is Lange's rate. And let us now contrast it against vacuum decay. So the formula is pretty similar, but the physics is quite different, which is hopefully clear already. So firstly, there's no analytic continuation in order to obtain this fluctuation determinants. One just integrates over this transition surface. So there's no integral over this instability. All of the configurations that are present here are actually physical and can occur during the time evolution of the system, unlike this bounce which lives in Euclidean time. So this critical bubble is actually a physical static configuration. And finally, the time evolution kappa, this exponential time evolution, actually affects the rate. So now that we understand nucleation theory, or we have now overviewed it, we will go on and use this to obtaining the rate in high temperature quantum field theories. So firstly, we will find the equilibrium distribution by finding the Hamiltonian for the system of these classical fields and of equilibrium particles. Then we will find the nucleating distribution and the corresponding probability flow using Liouville equation. And then we will obtain the nucleation rates and analyze its results and its features. So firstly, in order to get the Hamiltonian, we will need to introduce the canonical momentum, which appears here, here, and here. So it actually sources this of equilibrium particles. There will be no canonical momentum for the of equilibrium particles because its evolution is already first order in nature. So the effective Hamiltonian for the system takes this form. There are these basic field theory structures that one would expect to be there. And then there's also this of equilibrium particle term that will be related to statistics, Bose-Einstein and Fermi-Dirac. And there are no cross terms present in the Hamiltonian, which might seem perplexing. But this is truly the Hamiltonian, and it's conserved under the time evolution given on the previous slide. And one can actually show that this is the Hamiltonian and not only a conserved charge by introducing these Poisson brackets here. And with these Poisson brackets, one can get the time evolution of the system from this effective Hamiltonian. However, this is not really relevant to our discussion any further. The equilibrium distribution is then given by this effective Hamiltonian. And it's nice that there are no cross terms, because this means that the distribution factorizes into different pieces that we can do sanity checks on. So firstly, there's this conjugate momentum part, which is the basic one that one expects to be there. Then there's this equilibrium distribution in green for the field. And we know how to derive the equilibrium distribution from high temperature dimensional reduction. And so this is now a connection to these equilibrium methods. In some sense, we have now derived that you can use this equilibrium potential here for computing nucleation rates. And this in particular, this makes a connection to these effective field theory methods in equilibrium. And finally, there's this of equilibrium particle term. And if one were to compute the fluctuations of these particles, they would be exactly the same as in Bose-Einstein and Fermi-Dirac statistics. So now we have been able to do sanity checks for the equilibrium distribution, and like it seems physically very consistent. Now, after obtaining the equilibrium statistics, let's zoom onto the nucleation barrier. So we are linearizing around the critical bubble here, whose equation of motion is here. And so the dynamical variable now is given by this, the previous dynamical variable subtracted by this critical bubble here. So fluctuations are on critical bubble. And in particular, the equation of motion for the conjugate momentum becomes now linear in fields. And the Hamiltonian density has now a constant term from the critical bubble, giving exponential suppression for nucleation, and then quadratic fluctuations around the critical bubble, which then enter this fluctuation determinant. And now the system actually becomes analytically solvable. So obtaining the nucleation distribution, we should solve the Liouville equation. As mentioned in the classical nucleation theory section, we assume that the nucleating distribution is time independent. So Liouville equation takes this form, and its boundary conditions are such that it is in equilibrium on the metastable side of the potential barrier. and has a 0 value in the stable states. So in some sense, this equilibrium value in the metastable states, it sources the nucleation over the barrier. And now I will describe the result for the nucleating distribution. So it's, in some sense, it's just given by this thermal flow from the metastable states towards the stable states. Here's the same information in two different ways. So one is in figure form and the other one is in equation. I will first go over this figure because I'm a figure lover myself, and then explain the equation. So here's a 2D slice of the phase space. I'm neglecting all of the of equilibrium particle dimensions because they are not so relevant for intuition building. But I'm also neglecting infinitely many dimensions in the field space and in the conjugate momentum. So I'm focusing only on this dimension that kind of interpolates between the metastable phase and the stable phase. But those are far away from this figure. And in between the phases, there's this critical bubble around which there's this potential barrier between these two phases. And so there's incoming thermal flux because of the boundary condition on the side of metastable phase. And some of these configurations are deflected back to the metastable phase, where some others have enough energy to go over this potential barrier and start accelerating towards the stable phase. And then because of the boundary conditions, there's no flow from the stable side of the potential barrier that would deflect back to stable phase or anti-nucleate towards the metastable phase. And here's the same information in this equation form. So the system is in just pure equilibrium on the side of this side of phase space, and completely zero on the other side of this U equals 0 barrier, which is a plane that separates the incoming thermal flux from the metastable phase. So the flow from metastable phase is in thermal equilibrium, and it gives us the nucleation, is the punchline. So how to obtain the nucleation rates from the thermal distribution? It is the rate of the nucleating probability flux. So we just integrate over this barrier and get the flux. The probability current is given by the phase space velocity times the probability distribution, and we just integrate over the surface, and we will obtain the result, which matches Lange's results. So there's exponential suppression from the critical bubble, fluctuations around the critical bubble, and the exponential growth rates. So Lange's formula seems quite universal, and it is a result of this analysis. And importantly, the equilibrium part here, it remains unchanged. So the analysis we did back in the day holds even when of equilibrium phenomena is taken into account. However, this equilibrium analysis cannot really consider this kappa exponential growth rate consistently, because that is still affected by these off equilibrium particles. And let's look at that now. So the equations of motion for this exponentially growing configuration, they simplify greatly because of the exponential growth rates. So time derivatives only drop this exponential growth rate in front. So it appears here, here, and here in these equations of motions. And now just solving this system of equations numerically gives the exponential growth rate results consistently. Now let's just analyze this a bit further. The exponential growth rate configuration looks something like this. So there's equilibrium particles coming in, and then the field grows exponentially, and it pushes these particles out of equilibrium. This is given by this term inducing this of equilibrium particles. And then again, this of equilibrium particles go in here, and they give a back reaction that hinders the exponential growth of this background field configuration. And so this is the effect is that it makes this exponential growth smaller. One important thing is to note is that there's no reason for this to give exponentially slow exponential growth. And so the equilibrium considerations of the logarithm of the rate, the leading terms in it will be still consistently obtained by this equilibrium considerations. And another feature of this analysis is that we will see that there's a bosonic IR divergence, which makes the bosonic classical fields contribute more to the damping of nucleation than these particles. So the source term for these of equilibrium particles has a factor of energy derivative of the distribution functions, which makes the bosonic particles and the bosonic fermionic particles behave differently. One can solve for the energy dependency of this of equilibrium fluctuations, and then one sees that the effects onto the fields come through these energy integrals. For fermions, they are IR finite, but for bosons, they are IR divergent. And this means that the fermionic contributions, the dominant ones, come from the thermal scale, which corresponds to particles, whereas the dominant bosonic effects come from the fields, which live in these energies much below the temperature. So the bosonic fields are more important for damping than the bosonic particles. And in the article, I've shown how to separate out this particle scale in these exponentially growing configurations easily in dimensional regularization. Another feature of this exponentially growing configuration is that Boltzmann equations are actually okay. Previously, we had the problem that the fluctuations die down because of this collision term. And when there's no fluctuations, there will be no nucleation either. But now that we have our results and see that the particles only affect this exponentially growing configuration, we can add it back in post-production. So this exponentially growing configuration has already nucleated. So it has no need for fluctuation. And indeed, it has no incoming fluctuations whatsoever in these particles. If there was fluctuation, it would die down because of this incorrectly for the total nucleation. But for the exponential configuration, there is no incoming fluctuations. And so it does no difference for it. We have not really derived that Lange's formula holds, but we have already seen that it's pretty universal. That it holds for this very different system, and also introducing this collision term here. The underlying system still manifests these aspects such as fluctuation dissipation relation that make it seem reasonable that Lange's rate would hold with this addition as well. Okay, so now let us summarize the talk. So we have managed to compute the high temperature nucleation rates with of equilibrium particle effects. And it takes this Langerian form where the particles affect the exponential growth rate. And hence this also corroborates the equilibrium studies of nucleation rates, where this statistical part remains unchanged. And we also found that the bosonic fields are actually more important for this exponential rate being damped than the particles. And now for the outlook. This study sets up for more studies on realistic models and the effects of particles on these quantities, the duration of the transition and the nucleation temperature in more realistic standard model extensions. In addition, one can use these particles maybe to address the question if Lange's rate is applicable. That's all, if this scheme of classical nucleation theory is applicable. There was quite recent work in which it was suggested that the field has to thermalize in short enough time for Lange's rate to hold, and it's given by this energy of the critical bubble over the temperature and the exponential growth rate. And one can use these particles in future to study whether this equation holds. However, I still find this maybe a bit hypothetical, this actual relation shown here. And then this also motivates to find the bosonic field damping onto nucleation rates, whose blueprint is given by this Andreas Eksted's article from 22. Okay, thank you everybody for listening for my talk.
Thanks, Joonas. Thank you very much for your talk. Yeah, that was great. Very interesting, very informative. I guess let's open the floor up to questions. Do we have any questions? Please raise your hand on the Zoom thing. Okay, Mark, go for it.
Well, yes, thanks for very nice, clear talk, and yeah, it's a very interesting idea to apply Boltzmann to tunneling. There was a thing I think I missed. I'm sorry. It's like an explanation in the Boltzmann equation that you only included the dt phi term on the right hand side in the sort of the force term, and I was expecting to see a v dot grad phi there as well. I just wondered why that. Yeah. So that was one example. There we go. Yes.
Yeah.
Not there. You flashed past the thing that I was there. So in the Boltzmann equation on the right hand side, the force term, there's only dt phi. Yes.
Oh, the gradient.
Right. Yes, I was expecting to see a v dot grad phi there as well.
Mm-hmm. That's an excellent question. So the thing is that if you insert this equilibrium distribution in here, these two terms will cancel out identically for the equilibrium distribution, because it is if the background mass was not changing, equilibrium distribution is static, right?
Yes.
So this term in equilibrium, in static equilibrium, is 0, and so are these two terms as well. But now, because the background is changing, these two actually still cancel identically at all times, but then this term is left out because of the changing background, and hence we get this term remaining on this side. So there's +0 from the force term cancelling with the gradient term on this side.
Okay,
the
thanks.
Distribution.
I have another question, which is that so you did this for a thermal state, but could you apply this for any state? So something that was extremely non-thermal.
That's a good question. Not directly, because this relies heavily on the boundary conditions, and the equilibrium state in here is time independent, and so the boundary condition on this side or in this corner is just equilibrium. But then if we had some other distribution, it could be that this changes wildly, and then it might not be possible to have this static distribution, which comes from the static Liouville equation. So there might be this time derivative of the nucleation distribution on this side.
Yes.
That matters.
Okay, thank you.
Any other questions? Okay, we have a question from Bogomila.
Hi, thanks for the talk. So my question is, because I didn't fully catch it, maybe you said it. So with this formula and your approach, can you really compute this kappa, the dynamical prefactor, better than what was known?
Oh, yes. We can compute the kappa. So so let me back up a bit to have all of the equations of motion. Well, here. So if we want to compute the kappa, it is this exponential growth rate of this exponentially growing system. So we can just insert this exponentially growing configuration in here and in here. And what it does is that because it's exponentially growing, this derivative in time derivative will just yield this kappa here. And then we can cancel out all of these exponentially growing factors in the linearized system of equations. And then we will end up with these two equations here. And these can be solved numerically to get this kappa as well.
I see. And have you maybe tried doing it for some?
Yeah, I've actually tried doing it for this, just using this fermion. I didn't go into, I had pretty mild couplings when doing it. And I received a factor of 2 change in here. So the rate was halved, which still means that the equilibrium logarithm of this it still holds, like this logarithm receives a correction of log 2 from this. But I would assume that in more realistic models where this Boltzmann term, the collision term, is important, then it might contain the particles that go out of equilibrium on the bubble, and then the rate will be slowed down much more. Or if I push the couplings larger in general, it could then affect this kappa strongly.
I see. Okay, thanks a lot.
Thanks again. Yeah, Miha, go for it.
Yeah, thanks for this super nice talk. So in the example that you showed, you had a scalar with phi cube and a fermion coupled with a Yukawa. Have you thought about gauge bosons?
Yes. So a bit. So I think the end result should still hold for these gauge bosons, these particles, and in general, actually, it would hold that the bosonic fields would give majority of the damping from these gauge bosons because of this IR divergence discussed here. So this IR divergence for bosonic fields, and so the bosonic fields and particles, there's IR divergence, which implies that the bosonic fields give more of the damping. This can be used to study the damping from these gauge particles independently of the fields, but the main contribution comes from the fields.
Okay. Yep. Thanks.
Mark, you have another question?
I think you're muted.
I am muted, but my mouse is moving extremely slowly because of Zoom. Yeah, so I was expecting to see some. Well, I was hoping to see some sort of diffusive evolution happening as a result of taking into account this sort of thermal thermal effects, because that's sort of what happens when in Svalron rates and on the lattice and so on. So, is there something that you can shed light on? Can you shed light on that prejudice or intuition?
Yes. I hope that I'm understanding correctly. So there is still dissipative evolution happening, because these particles, they come in to the bubble and then they are deflected out of equilibrium, and then the particles continue moving out of equilibrium, out from the bubble. This exponentially growing configuration shows this tail going down, but this is because it's a like fixed time slice. So these particles move here, and they are now this much off equilibrium. But when these particles, they move out, then they will be more out of equilibrium here. So there's this dissipative phenomenon still happening, but diffusive. Yeah, I'm not sure if I understand diffusive as a concept correctly here, but there's
not growing exponentially. I think I think for example, Svalron rate and so on is quite a different thing from the dynamical factor is quite different from the exponential growth factor.
Well, the all of the configurations, at least in this linear theory, they will grow asymptotically exponentially. So there will be exponential growth, but it shows up not at the barrier maybe. So, but could you yeah I'm not sure if this responded to your question satisfactorily, but
it was probably a bad question, but yeah, well, since you're just over there, I can ask you about it more later. Thanks.
If I can chime in on the end of that, maybe what Mark was expecting is that somehow the bubble crosses this critical bubble, or crosses the critical surface, the separatrix, the whatever you want to call it, many times as it sort of wobbles around.
Okay, I see. It actually, I think it does. It does that. So this, so this is the idealized exponentially growing configuration that will arise from averaging over multiple configurations. But yes, these particles do indeed make the evolution jittery. So there should actually be many more dimensions here, indicating also these particles coming in, and they have this Bose-Einstein, they have these fluctuations, and they will give random kicks to the field evolution. So that will actually happen. That there are these kicks that make the bubble go back and forth.
But so somehow this back and forth is an important part of the calculations on the lattice, if you didn't take it into account. But
I do. Oh yes, that's also maybe.
But maybe that's already there in this calculation.
That is already in there. So it comes in maybe, let me see here. So this rate flux, this has this this evolution for this. So the evolution is actually jittery when taking into account this final dimension. But so these are really jagged lines actually in the configuration space. I've just shown smooth lines to aid out intuition that they will bounce around because of these particles kicking the bubble.
All right, thanks. I see Kari's got his hand up. So
yeah, Kari, please go for it.
Yeah, I would think that you coarse grain quite a lot here for the effective potential. So as you should, of course, and therefore you kind of kill lots of these small scale fluctuations from the bubble, whereas on the lattice simulations you include all of these UV modes, and that gives much more jittery trajectory there over the barrier, and that explains some of maybe the differences here.
This is actually not the case here. If you look at this thermal equilibrium distribution, there is no derivative term for these particles in here. So each space-time location is completely independent of one another. They are completely this is just white noise. So it's like ultimately jagged. So jagged. So there is actually this noise on all length scales in here. In this effective description.
Right, I see. Yeah.
Yeah. So it's
for the effective potential, you did coarse grain.
Yes, I did coarse graining, but it only took into account the equilibrium distribution of the particles, and I left this out of equilibrium particle still as a free variable.
Right.
And this equilibrium distribution, they are smooth because of the background field is kind of smooth. So maybe this illuminates more Mark's question, that there is this, like these are completely independent at each space-time location. No, in each spatial location of space-time, and then there will be this jittery motion, or in this field because of this influence, but it doesn't show up in this analytical analysis.
Okay. Seems like we have no further questions, so that's all. Thank you very much. Let's thank Joonas again. And yeah, I guess wish you all happy Christmas. We and you'll be receiving an email from us about the upcoming seminars. So yeah, thank you all very much.